From this point on, everything I say and everything that's projected on the board is being recorded. Now, where we're going to begin today is with the new blackboard. Any of you realize that there is a new blackboard? There's a new version called Blackboard Ultra. It, from what I understand, for students, there's not too much difference. The main difference is before we had a series of tabs here. You almost had to know what was in each tab and what tab to do. Now you'll see everything there. So this is, I don't know how this is the instructor side. I don't know how the student side looks, but I think you probably have some, like a tab that says courses. That's what you click on. And then here's our course, Math 113. I'll click on that. And this is everything within the course. Can I get your name, please? Okay. And let's see. You were here last time, right? Yeah. I've had so many people adding. Everything's cramped in little spaces here, and I want to make sure I've got everybody covered. All right. So this is our course. Notice not that many tabs over here. Everything is here. You don't have to remember where is the syllabus, where's the locator card. It's all here. Now, last time we talked about the syllabus, didn't we? Those who were, two of you that were here. We finished the syllabus, right? Did I finish the locator card? Okay. Did we talk about research paper instruction? Say again?
I think so.
You think so? Okay. All right. If not, it's here. But if you didn't hear it, I'm going to skip over it if we did talk about it. You think we did?
Yeah, I think we did.
Okay. All right. But you can click on this in just a little bit. Now, did I give you the WebAssign code?
Yeah.
Oh, I did. So that means we did do the research paper. Okay. For those of you, let me just show you an example of how you do this. Let's go to syllabus. Okay. And the old Blackboard, if you clicked on this, it opened. Or if it went to a screen like this, you clicked on that, it would open. This one you have to, at least I understand from other students, you have to come over to these three dots here, click on that. Now you certainly, I hope, can't edit my file or delete my file. Please don't. But you only have this option here, download the original file. So that's what I'm going to show you how to do here. And then this is a little tricky sometimes. I have to pay attention. Sometimes this is all you get, and you click on that and it opens. Now, between Blackboard and Microsoft, they are really, really slow. That's not what I just clicked on to open. This is what's opening now. This is the syllabus. That's my locator card we've already done. So I'm going to go on and delete that. And sometimes it gets hung up, like it just did here. And what I have to do then is a Control-Alt-Delete and start the task manager. And usually okay, now it says, there it is, there's the syllabus. It usually will make it start, okay? Now you can't edit my thing, but there's the syllabus. We talked about it last time. I probably did some updates since we met last time. I know, for instance, the office hours down here I had to improve on. And I also had to do the start time for the class, start and end time for class, because that was a previous several terms ago. But anyway, there's the syllabus, and that's how you get to it. All right. Now, we've already done the locator card, but that's what I'll show you next. Okay, this I don't need anymore. Okay, so that's how you open the syllabus. Now, when you're through with the syllabus, go to the blue box up there with the white X in it, click on that, and you go back to your course content. Syllabus locator card was what I just deleted there too. Research paper instructions. Again, you click on this, and then when you see the file there, then you click on that. Okay. WebAssign code we did before, but this is really easy, so I'll go do this. Now notice I'll show you in a minute. Here's a WebAssign code, okay? Now, if you're doing Cengage Unlimited, you probably need this. If you want to do WebAssign, I'm never going to make an assignment in WebAssign. However, if you want to use that, if you find it useful, you like the tutorial help, it's a good package. The things are out there, you can certainly use it. I will not be grading it. I will not, it's only for your benefit. So use it if you want to. Here's the code. Now, the class key, this is just what's called the class key. Don't do class key. You do Lawson.al space 2994 space 3399. Okay? That's your the class code. And this is Jacory, right? No. Oh, David. Okay, got it. David Nash. All right, good deal. Now, there's the class key. We did it last time, but I'm showing you again because that was real easy. Okay? I'll get out of that and go back to this. Okay. Now, what I was starting to say, and this is for, these are documents. This icon here means a document. It may be an imported document that you could upload or just a single line or two like we just had with the class code. What this is a web link. Okay? And you see the little chain there, links in a chain. What this indicates, this is a folder. Okay? Now, did I show you how to access YouTube videos last time? You remember? I want to do it anyway because we've got 3 new people here. So if you go to the Math 113 YouTube video, click on that. The web links go straight to the link. No uploading anything else. They go there. It may take a few minutes, but they do go on the YouTube. All right. Now, there's already a whole bunch of files here. We've only had one class. Where is that class? It's at the very bottom of the file. Okay? There it is. This was last Thursday's class. You click on that, you see and hear everything we talked about the syllabus, about the locator card, about the research paper, about the WebAssign. You see it all. Okay? Somewhere there we stopped. You may say, why are all these other files there? Those were left over from the last time I taught the course. Why have I not deleted them? Am I just lazy? Well, yeah, I'm lazy, but that's not why. The reason is, it has happened more than once that I've come in to teach a class, and for some reason I can't access Screencast-O-Matic. One time, the business office forgot to pay the bill, and they cut us off for about a week and a half. So I didn't have anything. I started leaving them up there. So at least you can see what we did a term or two ago. So that's why I leave them up there. We've had other times the server has gone down. The supercomputer at Huntsville has gone down. Something else is that my computer may screw up, and I can't do it. I can't save the file that day, so I'll leave them out there. So this one, the research, even though we talked about the research paper last time, this we actually may have got started in 4.1 or wherever. This one was one we did a couple terms ago that that was the last one we hit. We didn't get that far last time I taught the course, so that one's still out there. So these are 2 terms ago. This is the last time that I taught it. Okay? And some of these are not in the right order. But anyway, we will, that's it. So you can go back, you can see things that are going to be happening in the future that actually happened in the past. But always the most current things are at the bottom. The older stuff is at the top. And this is Jacory, right? Okay. All right. So we're still missing Amari, and I can't read my writing here. Tanu Sherelle Johnson. She was added, I assume it's a she, added to the class when I put in attendance, but she was not here at the beginning of class, but she was by the end of the day, but I still haven't seen her. Same thing for Aaron, but he is here. And Amari was added after, but he's not here either. Okay. All right. So there is how you access the YouTube videos. Again, the most recent things are at the bottom. The previous things are at the top. All right. So you can go back and see and hear everything we talked about in class on Thursday. All right. Next is the folder here with the PowerPoints in it. Now these are all the PowerPoints we could possibly do, probably many that we won't do or some that we won't do. I don't know. Oh, okay. So anytime you have a folder, you see this one other icon here or symbol here, that opens the folder. Or you see it, made it look like the folder open a little bit. And here they are. There's 4.1, 4.2, 4.3, 4.4. Chapter 4 is a long chapter, 4.5, 4.6, 4.7, and 4.8. It is so long that I'm going to give you a test on the first 4 sections and then a test on the last 4 sections. So you have 2 tests in chapter 4. Okay? Then 5 is 5.1, 2, 3, and it has to catch up a little bit. There's 5.3, 4, and 5. After we finish those, you'll have a test on chapter 5. Then 6.1, 6.2, 6.3, 6.4. You saw one term we got as far as 6.4. The next term only went probably as far as 6.3. So that's why those things were out there that way. 6.5 is as far as it goes. Now, last time before some of you got here, the rest of you spoke for you. You're stuck with their decision. They said they preferred take-home tests to in-class tests. Sorry about that, but they will be take-home tests. Okay? Can you live with that? Okay. Too bad. Okay, never mind. All right. So anyway, there are your PowerPoints. I'm going back up to the top and close those because it strings things out so badly. Is that the only place PowerPoints will be seen? No. They're also seen in the YouTube videos because I teach from the PowerPoints. Those that I just showed you are static. You just read them. You can look at them ahead of time. You can print them out ahead of time. If you want to take notes on them, that's fine. Whatever you want to do with those. The ones in the YouTube videos, you hear me talk. You see me write. You see I have a tablet PC. I write with an ionizing pen. You'll actually see me working exercises and things like that. So there's the PowerPoints. These next 3, and these again are web links. They're just various web sources that either I found or students have told me about that they like, and they support the course. Okay? Now, some of these, like Education Portal and I think Slater, refer to the book, but they refer to older editions of the book. The last time I looked, they hadn't updated to the new edition. They may now. If you go to them and find out they're more current, let me know, and I'll put them more current. The Prof. Rob Bob, he's sort of corny at times, it seems like, but it's sort of like Khan Academy, that type of thing. They just discuss how to work certain types of problems. Okay? Not related necessarily to this book. So that's the course. Any questions? All right. Now, I think I'm through with Blackboard. So, I don't know what it just did there. Say again? Research paper. What's your question? Yeah, just a page from one of your resources. Sources. Yeah, a single page. If it's a book you got out of the library, you just go and print me, take it to the copy machine, copy a single page. Don't need the whole article or anything else, just a single page from one of your sources. Something you got off the internet, just print a page. Now, if it happened to be a website like a YouTube video or something like that that you can't print anything from, just give me the link so I can go to it and verify that it's real. Okay? And if it's a good one, then I'll put it, next time I do the syllabus, I'll add that to the syllabus. Okay. All right. So I think I'm through with Blackboard. Okay, here we go. I wondered where to get out of this. Hit on the blue box with the X in it. That closes out, and then you can go to any other course. Now, my other two courses, I think I finished everything on those, so I'm going to end Blackboard here. All right. Now, before we start actually what we're going to be doing, pre-calculus trig, there is one other topic that we need to address. This topic has 3 subtopics. The topic is safety. Now, there's nothing we're going to be doing in this class that should be hazardous, okay? Nothing. But safety involves things that's not just going on in the class. What are one of those 3 areas of safety we always have to keep in mind?
Fire.
Fire, exactly. What if, and that could include things like chemical spills or something like that. What happens inside the building that we need to get away from? Okay? That's the first. Now let's take the worst case scenario, that it starts here. Say my computer explodes. It starts arcing and sparking, catching pieces of paper on fire, maybe even the desk. What do we do? Say again? Okay, yeah, he wants to get out of the classroom, let the building burn down, don't let us another soul know, but we get ourselves out, right?
You pull the fire alarm.
Oh yes, we want to pull a fire alarm. That leads to the question, where is the closest fire alarm? Now on this little diagram here, this shows the second floor of this building, and here we are in this classroom right here, on the classroom here. Now, where is the closest fire alarm to us? Any ideas? Let me give you the bad news. Everything you see here, this hallway here, that hallway there, this is the oldest part of the building. Built before fire alarms were put. There are no fire alarms. Any of these hallways that you see from that. But there are closed fire alarms. Here's what you do to get them. And I would suggest 2 people do it. In case one falters or forgets, the other one can do that out the home. Okay? Go out the door here, hang a left, go down this half flight of stairs you see right over here, and then when you get down, go past the restroom, and that corridor leads across to the new part of the building. Now, this new part doesn't show up here because this is second floor. That new part is first floor, even though it's the same level as the second floor here. Okay, when you go through those gray double doors there, right in front of you is financial services. You know what we're talking about? That's the newest part of the building that has fire alarm. You either go to the left or to the right, fire alarm in sight, both places. Y'all go and pull the phone. Okay? So that's one way of notification, something we do first. Okay? But we just don't want to pull a fire alarm. What's another good thing to do? Somebody who's still in the classroom. Yes, you got your cell phone. Okay. Now the very best thing to do, most of the doors leading into the building, at least they used to have, I know the one I come in is nearby, there is a 8.5 by 11 piece of paper which has the campus police numbers on it. One for Birmingham, one for Bethel. Good idea to put those on speed dial on your phone. Emergency number. Now if you don't have it there, then 911 is the next best. So whatever exit you take today, see if you can find those numbers. Or go by campus police and get the number. I think it's posted on their door. You can go in and ask them. That number is not the office or anything else. That's the phone that whoever the duty officer is guaranteed to have it on his or her person. 24/7, whenever there's a duty officer here, that duty officer has that phone on. That's the number. So somebody here, dial them or dial 911. So the alarm is to help other people get out of the building. The 911 or the campus police, that's to get emergency vehicles. Okay? So, we've notified. Well, my papers are still burning here. Anything else we want to do? You don't care about my computer second?
We got to go out there and pull the level. So, that's all.
Those sprinklers here either. What what's next best? No sprinklers? Fire extinguisher. Yes, ma'am. Yes. Okay, well, let me pause this. Okay, about safety, and I think we finally determined we ought to try to find the fire extinguisher. Does someone know where the closest fire extinguisher is? Very observant crowd, obviously, because if I step out the door here, 5 feet from where I'm standing here, it's right there on the wall. You can't get much closer than that. If someone go out there, I know that probably some of you guys, you're all guys, you probably thought, hey, wouldn't that be cool to break that glass down? Now you get to do it. If there's a fire in here, you get to break the glass. Bring it in. I handle it. If you don't know how to handle a fire extinguisher, I'll deal with that. Okay, so we started putting the fire out. We pulled the alarm. 1 or 2 people go down to do that. At least one person has called 911 or campus police to let them know what's going on. Now what do we do? Back to your original answer. Get out of Dodge. All right? Okay. We will evacuate. Now, this is where we pick up if we hear the alarm. We hear the fire alarm. We don't have to worry about the other thing. Someone's already done it. We don't even know where it is or anything else. We just evacuate. What do we do? Where do we go? Here we are in the corner classroom here. We'll hang a left, go out the door, hang a left, go down the half flight of stairs, hang another left, go down the full flight, and then when you get at the base there, get out of the building. There's an exit right there, and you leave the building. And go straight out of the building, okay? Don't move along the wall, because if there is an explosion or something, glass is going to start flying out of the building. You get away from the building as quickly, safely as possible. And it's sort of hard to see here. Here we're in this classroom right here, underneath the roof right there. And we go, everything from this wing of the building goes down to this parking lot right here between here and Huffle Hall. That's plenty of distance away from the building. Day like today, it's going to be pretty miserable, okay? Raining and stuff like this, but we'd be safe. We go to that parking lot. Now, if I'm fighting the fire, I'll be doing that. But if it didn't start in here, and you all look pretty healthy right now, but what if one weekend someone twists a knee or an ankle or something like that and are a little hobbling? I will be with the slowest person leaving the classroom. But what I also do will be taking my roll sheet, okay? And when we get out to the parking lot, we'll gather as a group. I'll call roll again. If anyone's missing, that means somebody has to go back into a burning building or a chemical-spilled building to try to find it. So stay together. Don't say, hey, building's on fire, I'm out of here. If we don't know where you are, someone's risking their health or their life trying to locate you. So don't leave. Wait until we call roll, we account for everybody, then I count to the honchos of the building and make sure everybody is safe. And then they'll let us know what to do. Once we've accounted for everybody, if it's a day like today, and that building's not on fire, we're going to go down and get somewhere in shelter there. Okay? We're not going to be back to this. Oh, it doesn't look like it's too bad. No. We go to someplace safe. If one person is parked there, we might get in the car or something, but we'll try not to make you sick just by being out there. Okay. Any questions about fire then? The key is, once you've made all the things like fire extinguisher, alarms, 911, you get out of the building and go to that parking lot down there. Now, it's been a few years since we've had a fire drill. We got real fired up about it for a while. And what they had us do in the fire drill is everybody goes to the wrong door. Well, not everybody, but most of us did. I said, no, you don't practice doing something wrong. You practice going to the right place. Then, if you want to meet as a group, we'll meet as a group. And after that, they decided not to do any more fire drills. I don't know. Maybe we will have one. We'll see. Okay. Any questions on fire? So that's one safety issue. Think of another one.
Tornadoes.
Say again?
Tornadoes.
Tornadoes, exactly. Inclement weather. Okay, now that nothing initiates here, we'll hear the alarm. And you hear it really clearly from this room. Okay? What happens if you hear that? What do we do?
Go to the lowest.
Lowest level, interior. 2 words to keep in mind. Lowest level, interior. How do we get to the lowest level interior? Well, you go out the door here, hang a left, go down the half flight of stairs, hang another left, go down 1 full flight. This time, rather than going outside, you go inside. And the first floor looks a lot like this one. It's a little bit different. But right in front of you, the stairwell there, you'll see the restrooms. And actually, the restrooms are not a bad place to be. Okay? The walls are close together, and you have lots of corners. The greatest strength of the building is in the corner. Okay? And close walls are next best. Here's another key. Now, this is second floor here. If you get down on the first floor, the back wall here to that part of the building is soil. Okay? There is no room on the other side of that. That is a stronger wall that you're going to find. So the back wall is a pretty good place to be. Now, you may not want to spend the next couple of hours in the restroom. And if you don't, that's okay too, because there's other good places to be. Right next to the restroom, actually there's 1 or 2 more steps down. And then you get what's underneath this corridor is the dean's office. Now, if she's in there, or the associate dean, or anyone's in there, and they invite you in, you can certainly go there. Again, that back wall is a very, very secure, strong wall. There's lots of corners in that room, so it's a pretty safe place to be. But most of the time it's locked, so don't break it in or anything. Go down. Next room down that hall is room 160, which is the developmental math classroom. Okay? Now, the disadvantage there is a big open space like this. You don't want to be in the middle of that. If something falls through, the strength is in the corners and that back wall. So along the back wall, or any wall, and the corners, that's the safest place to be. Out in the middle, not the best place. But it probably will be okay. Okay? Then you go through those glass doors in the hallway there and go into the library area. Immediately to your right is the computer room. Okay, so the walls are closer together, smaller room, lots of corners, especially that back wall is very secure. The corners are good, everything's good in there. Okay? Now, right next to that room, the computer room, is what I call the reference room in the library. Again, that back wall is very secure. The corners are good. Now, it does have bookshelves and stuff, and there's some rocking and rolling going on. Things could start falling, but usually that's going to be pretty safe too. Don't go any further into the library, because then you start getting exterior space. As long as you're low level, interior, you're good. Now, I left off maybe what the best choice is at all. That's the hallway. The hallway doesn't have any corners, so that doesn't have to fight the string. Doesn't have that secure back wall. But here's what the hallway has that nothing else I've mentioned has. Emergency light. Because the odds are, if we have severe weather, the power is going to go off. Right? Now, last Saturday, we were shocked. In our neighborhood, if there's any wind at all, usually the power goes off. Because we've got lots of trees and something is going to go down. We didn't lose power at all, but maybe 100,000 or so other Alabamians did. So we were fortunate with them, but most of the time the power will go out. If the power goes out, you're in the dark, except for the hallway where there's emergency light. So that's what makes the hallway an attractive and safe place to be. The walls are close together, it's an interior space, but there's just no corner. And that back wall of it is not secure to the back wall of the place. So that's what we do in case of weather emergencies. So there's fire. You get out of the building, weather emergency, you go lowest interior. What's the third safety situation?
School shootings.
Yes, active shootings. A few years ago, I never would have even thought to mention it. Things have gotten crazy. Now, remember, I'm hard of hearing, okay? So you'll probably hear it before I do. If you hear rat-a-tat-tat, and it sounds like gunfire, stop me in my track. What do we do?
Lock the door.
Okay, lock the door. Unfortunately, I do have a key for this door. Okay? However, there's no way to lock it from inside. There's no keyhole. Even if you crack it open, there's no button to push. I have to go outside and find the key, and get it locked. Then you don't close the door. I pull back inside and close the door. Okay. A little issue here. There's another entrance to the classroom. Okay, that's to the next classroom. Now, this door does have buttons right here. I press the button and this door locks. But it locks from the inside, not from the outside. This doesn't do us any good at all. He can get in, we can't get out. So don't lock this door. Now there's another door here, one to the next office. It has a deadbolt. And if I had a key, we'd lock that one, but I don't. Okay, I cannot lock that door. However, the next door here does have buttons here. You know here? Yes. Okay. If you press that button, it locks from the outside, but not from the inside. So that's the one you press. Okay. Now, if that hallway door is open, I would go and close the door. I can't lock the hallway door for that classroom, but we can close it. Turn off those lights too, nobody's in there. Then lock that first door again. Okay. Close. We close this door because that has a window in it. He can look in here. We don't want him to look in. We want him to think this is a secure space. Okay, then we'll go on and close this door too, but we don't lock it. Now, what else do we do? Turn off the light so it looks totally dark.
And get against that wall.
Get against this wall. Y'all are in a really safe place here. You see, he can fire through the window if he sees anyone in here. He could probably fire through the grate there. Maybe a little more difficult. He could probably even fire through the door. I don't know how solid that is. He's going to have a hard time firing through concrete on the wall. So that's the safe place to be. He can't see us. The lights are off. What else have we done? Turn off the cell phone. We don't want to ring and say, hey, you okay? We don't want anyone getting in touch with us. We don't want to make a sound in here. So be sure you turn those cell phones off. Okay? We all get back here and we stay back there. Quiet as a mouse. Okay? We don't talk. We don't do anything. Maybe a lot of praying or what, but that's it. Okay? Until we hear it, all is clear. Okay? Now, if he does manage to get in here, you don't be a hero. Okay? Your futures are all ahead of you. Mine's just about all back here. Okay? So if anything needs to be done, let me take care of it. Okay? You're the future. I'm not. Okay? So you stay quiet, group together, stay safe, hold the desk up, whatever you can do. If anything has to be done, let me do it. Now, if I do get them down, you kick the fool out of me. No, I'm just make sure that weapon is secure before you make any movement on it. Okay. All right. Any questions on safety? Okay. I think that's it. So now we get to actually do trig. All right. I've already got the first slide up here. Like I said, I teach from PowerPoint. So let's go from the current slide. Any questions on anything before we get going? Just a couple things to remember. On the last page of the syllabus, which should be up to date now, you do have a acknowledgement page. You can either print that off, sign it, and turn it in to me, or you can type in your name and email it to me. Anything will do there. The other thing, your research paper, as soon as you can decide on a topic, hopefully this week, write your name and your topic on a piece of paper. If you want to give me your best phone numbers, if I do need to ever get in touch with you, I can have. Sometimes the numbers that are in the system aren't any good, okay? So you can give me those. If you go back and listen to the first day of class, I go through all that stuff, okay? So, any questions before we get going on the PowerPoint? I thought I had clicked on this and so forth. There it comes. We're starting in Chapter 4, okay? I assume all of you had pre-calculus algebra, right? And you should have recognized the book because this is the same book we use for pre-calculus algebra, but we did chapters 1, 2, and 3 for that. 4, 5, and 6 are pre-calculus trig. You may have done some in 7 in pre-calculus algebra. I usually don't get to that in my classes, but if you did, fantastic. 4, 5, and 6 are what we're doing here. Yes?
So the entire class is 4, 5,
I'm sorry?
The entire class is 4, 5, and 6.
Yeah. But 4 is a very long chapter, and we'll have a test midway through it, and then at the end, 4.1 through 4.4, we'll have a test, and then 4.5 through 4.8, we'll have a test. Okay. And y'all voted last time to do take-home tests. Okay. So, chapter 4, trigonometry. Anyone know what trigonometry means? Where they got the word? Metra, that suffix there, means to measure, or a measuron. And the TRI is basically started out the measure of triangles. That was originally what trigonometry was. Now, it's going to be a while before we even mention a triangle in the course. Because what we do, this book, and most other books do too, is start somewhere else. And the 4.1 is starting with radian and degree measures. These are the things we measure the triangles with, but we don't start with triangles. Okay? Where we start here is we will describe angles. We'll talk about radian measures of angles. We'll talk about degree measures of angles. And then we'll use angles to model and solve some real-life problems. Now, you're going to see this kind of outline objectives for every section, just about. We'll describe what we're going to do, use some of them, and then model them. Use them in real-life type situations. So let's start with angles. Not angels, not you guys, but angles. Okay. As derived from the Greek language, like I just said, the word trigonometry means measurement of triangles. Metra is measure. The TRI meant triangles. Initially, trigonometry dealt with the relationship between the sides and the angles of the triangles. Okay? And before this class is over, we're going to be dealing with just about any combination of sides and angles that you can have in any old triangle. However, we're not going to start with triangles. We'll start with something else. It seems a little bizarre, but it's true. Let's first talk about the angles. Now, a little bit of nomenclature here. A line, by definition, is infinite in both directions. But it's straight. Straight line, infinite in both directions. Wherever it's pointing, infinite in both directions. Now, what we're going to deal with to begin with, and not really very much, is a ray, which is a half line that starts at some point and goes infinitely in one direction. That's what we call a ray. Okay? Now, what we're going to do with that ray is rotate. Up, down, side, wherever. You're changing the orientation of that. Okay? That's what we mean by rotating a ray or a half line about its endpoint. Okay? The endpoint is that terminal side. Now, again, we're going to move off of this really soon, so don't sweat that too much. But the deal here, angles measure that rotation. Okay. So let's say the starting position of that ray, that half line, there's the vertex, that's the terminal end, goes infinitely in that direction. We call that the initial side. And then wherever we rotate it to, that becomes the terminal side. It's the same ray, it's just been pivoted about the vertex, that terminal, the fixed endpoint here, there. This is a measure of an angle. Okay? It's not a length, it's not anything but an angle. Okay? And that's how we define it. Okay? And for a while, we're going to talk about what kinds of units we use to define the angle. Okay? The endpoint of that ray, as I showed before, is called the vertex, and the perception of an angle fits a coordinate system in which the origin is the most handy place to put that vertex. If you put the endpoint there, then you can rotate around there, and everything pivots around the origin of that coordinate system. Okay? Now, the initial side, rather than having it down here somewhere, as long as you keep the relationship the same, put it on the positive x-axis. That's going to be what we call our standard position for the initial side. And then as long as that ray is in a plane, and it has to be in a plane, and you rotate it, the terminal side will then be somewhere else in the plane. If it's over here, we say it's in the first quadrant, second quadrant, third quadrant, or fourth quadrant. We'll get to those later, but we're rotating. Now, that angle is said to be in standard position. The vertex at the origin, the initial side on the positive x-axis, and the terminal side wherever it ends up being. Okay. That's standard position. Usually the easiest to deal with. Okay. Now, by the way, sometimes I forget to turn my pages to point things out to you in the text. Where you have your books or something, ebook or whatever. I don't know if ebooks have page numbers, but we're on page 260. Now, I'm not sure why this is true, but counterclockwise rotation generates what we call positive angles. You would think it would be clockwise, it's not. It's counterclockwise. Whereas clockwise rotation from that initial side, moving clockwise direction, that gives you a negative angle. Okay? It's just how things are. Okay. Angles are usually labeled with Greek letters. This is an alpha, that's a beta. The most popular one, just like your most popular variable in algebra is x, the most popular value for an angle is usually theta. Now there are plenty others you can use. Gamma would work, phi would work. They use phi's a lot. There are some really squirrely looking Greek letters, that squirrely names too. C, but those are useful. Alpha, beta, theta is usually the most popular. But sometimes angles are represented by capital letters. Usually a lowercase letter indicates a length. A capital letter in this context is going to indicate an angle. Okay. Now, there's your plus and minus angles, how we define that, whether you're going counterclockwise or clockwise. These are how you represent angles. And these are showing two angles, one alpha and one beta. But they both have the same initial side, that's standard, but they both have the same terminal side as well. This alpha, though, is what kind of an angle? Positive, because you're going counterclockwise. This beta is negative, because you're going clockwise. Okay? But these two angles are called co-terminal angles. They both have the same initial side. They also share the same terminal side, so we say co-terminal angles. Now, that's this alpha and beta. Over here, though, here's the alpha from your initial side to your terminal side. Now, notice something they quit doing. They quit putting the arrows on the end. Now they're just showing line segments. Those are fine, too. The first definition, like I said before, they talked about rays, but then they're not ever going to mention them again. So now they're just showing line segments, which will work fine, too. So here's the terminal side. But the beta is different from alpha. How? Alpha is?
Counterclockwise.
Yeah, so it's positive. Beta is also counterclockwise, so it's also positive. But they're still coterminal angles. What do you notice the difference is? Beta has gone one complete circle more than alpha did. But they're still coterminal angles. Now, depending on how you measure your angles, that complete circle has a very definite value. I don't want to get there yet because we haven't even defined it yet. But those are both coterminal angles. Hang on to the concept, okay? In this case, this makes one complete circle. When you add the positive value here and the absolute value of this negative value, you get one complete circle. Here, if you take the difference between the bigger angle and the smaller angle, you get one complete circle. Okay? So hang on to that concept. We'll talk about that more with coterminal angles later. What we've got to do is figure out how in the world we're going to measure these angles in the first place. Now, I forgot to say this early on. I think I may have said it last time. The battery in my watch died and I haven't had a chance to replace it. So I have no way of knowing how long I'm going. So if you will, please let me know when we get to, what is it? 11:15, right? Okay. So let me know when I reach 11:15. Otherwise, I'll keep going forever. Okay. I don't know how to stop. Okay. So let's do one type of way of measuring an angle. And that's called radian measure. You can determine the measure of an angle by the amount of rotation from the initial side to the terminal side. That's what an angle measures, okay? One way to measure this is in radians. Now, you might think, oh, that's a unit. No, it isn't really. I mean, we treat it like a unit, but really it isn't. What a radian is a ratio. Not a unit, but a ratio. We'll get to that in a minute. This type of measure is especially useful in calculus. I hope most of you are going on to do calculus at some time or another, right? Yeah or nay, okay? If you do, you'll find out most of the time when we're dealing with angles in calculus, we're almost strictly radian measure. Now, when we do, most of the things we do with angles, we usually use that little symbol, degree symbol. And we think in terms of degrees. But we don't use degrees much in calculus. So that's why we're going to focus mostly on radians. Okay. So here's what we do to define what a radian is. You use the concept of the central angle of a circle. And remember I said, even though trigonometry is a measure of triangles, for the first part of this, we're going to be dealing with circles, not triangles. And it doesn't seem like that should even relate, but it does. Okay. So let's say we have a circle here. We put the center of the circle at the origin, right where you put your initial side of those rays or line segments there. Put that. The radius of that circle is how far every point on that circle is from the origin. That's how we define radius, right? Now, we know this is the angle, and like I said, the most common symbol for angle is theta. There's your angle theta. Now, for that angle theta to be 1 radian in extent, here's what has to happen. This almost looks like a triangle, doesn't it? But it's not quite. What this is called is the arc that's cut by that angle theta. This is the arc length. That's actually a length. A radius is a length. This is a length. The arc is a length. And when the arc length that's cut by this angle is exactly equal to the radius, in other words, if you put either one of those two radius, bend them around there, they come exactly right there, then you have an angle of 1 radian. Okay? 1 radian. To define a radian, you use the central angle, that's your theta, of a circle. Got the circle there, radius r, whose vertex is at the center of the circle, and what you have when the arc length cut by that angle is exactly equal to 1 radius, then you have an angle measure of 1 radian. So what it is a ratio. It's a ratio of the arc length cut to the radius of the circle. So here it is. The arc length is when the arc length is equal to the radius, when that angle theta is 1 radian. Okay. Here then is the definition. 1 radian is the measure of the central angle theta that intercepts an arc S equal to the length of the radius. Algebraically, here's the way to remember. Theta in radians is S divided by R. Whatever, if that's a very small arc length, that's going to be a very small angle, something less than 1. That would be close to 1. This would be way more than 1, okay? And as much as you go, remember, the theta, to be positive, you're rotating counterclockwise. So this is how we define a angle measured in radians is the ratio of the arc length cut by that angle and the radius of that circle. When S is equal to R, then you have theta is equal to 1. S less than R would be a theta point something. A S greater than R, that would be 1 point something or 7 point something. Now, let's go back for a moment. This is what we call arc length, S. Does anyone know what the length is if you go one complete trip around the circle? Anyone remember what that's called? One trip around the circle. Say again? Circumference. Did someone say that? Excellent. Okay? Circa means circle, and I guess ference means measure. Okay, you've gone one trip around, that's the circumference of the circle. Does anyone remember how we define the circumference of the circle? There is a formula from geometry. Say again?
Pi r squared.
Now that's the area of the circle, pi r squared. What is the circumference of the circle? So it'll be a length measure. You see a pi r squared would be a square measure, which would be area. Anyone remember what the circumference of the circle is? There's actually two standard definitions for it. Anyone remember? The first one is pi d. Pi is still there. It's pi times the diameter of that circle. But since we're not dealing with diameters, we deal with radius. Pi is the radius associated with the diameter. Exactly half of it. So that would be 2 radii times pi. 2 pi r. That is the circumference of any circle. A huge circle with a large radius will have a huge circumference. A really tiny little circle is going to have a very small circumference. Okay? So it's 2 pi r. Okay? That circumference, or that arc length, one trip around the circle is 2 pi r. Right? This definition, if you were to multiply both sides of this equation by r, you'd have S is equal to theta times r. Well, if that's one time around, that is your circumference, and that would then be 2 pi r. So your theta would have a measure of 2 pi. One full revolution around the circle is always going to be an angle of 2 pi. Radius. 2 pi radius. So all the way around any circle, a tiny circle, a big circle, all the way around is going to be 2 pi radius. Always. Now, if that's 2 pi radians all the way around the circle, what would be halfway around the circle? 1 what? Pi. 1 pi. Pi radians. What would be half of that? Pi halves radians. Half of that? Pi fourths radians. And then any fraction thereof. So that's how we get our radian measurements. Okay? From the fact that the circumference of a circle, or the arc length of a circle, is 2 pi times the radius. So the angle would be 2 pi. So this then shows what we're just talking about a little bit. 1 radian would be the angle measured so that the arc length here is exactly 1 radius. Okay? So that would be 1 radian. Here would be 2 radians. Here would be 3 radians. Okay? Now, wait a minute. How do we know that's 3 radians? What did you say the distance halfway around the circle would be? What the angle measurement would be? Pi. 1 pi, right? And how much is pi? 3.1416. So this is just a little bit. 3 pi would be here. 3.14 radians would be right there. So yeah, 3 radians almost makes a straight line. Not quite, but close. So this would be 4 radians, 5 radians, 6 radians. Okay, which would be almost 2 pi radians. Well, 2 pi would be 6.28, blah, blah, blah. Okay, so yeah, there's a 0.28. This would be 6. That would be 6.28 radians. All right. because the units of measure for your arc length and your radius are always the same, really the ratio S over R, which is theta, has no units. We say it's so many radians, but really it's a ratio. It has no units. It's just a real number. Most of the time we'll say so many radians, so we'll know what we're talking about. But remember, radians really isn't a unit, it's just a ratio. All right. So again, the 2 pi is about 6.28. It's not exact. Why is it not exact? Pi is an irrational number. You can't express it as a ratio of two integers at all. It's a number, if you wrote its whole decimal, it'd be 3.141595, blah, 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 blah. Just keep going forever. You never repeat any unit of it. Okay? It's an irrational number, not a ratio of any two integers. Okay? So therefore, 2 pi is not an exact number, it's approximately 6.28. It's really 6.281, no, 32 or something like that. It goes on and on and on. Okay. Now, this is what we were saying before. Because the measure of an angle of one full revolution is 2 pi, because it's 2 pi r, which is the circumference of a circle, divided by r. The r's cancel out, and you just get 2 pi radians, or 2 pi. Then half a revolution is 1 pi, because 1/2 of 2 pi is pi. A quarter of a revolution is pi halves radians. A sixth of a revolution would be pi thirds radians. Okay? Because one complete revolution would be 2 pi divided by 6. Sixth of a revolution, that would be pi thirds. These are some really handy radian measures to keep in mind. These are going to be our favorite of all time angles, okay? And you will get used to them, okay? Used to see them. So here's the illustration of that. That would be pi 6, that would be 1/12 of a complete circle. That's pi 6. This would be pi, okay, this one would be pi thirds, this would be pi halves, and all like this. This is 1/6 pi, 2/6 pi, which is pi thirds, 3/6 pi is pi halves, 4/6 pi is 2/3 pi, 5/6 pi, and pi, okay? If you break this into quarters, this is pi, there's half a pi, this is quarter pi. There's a quarter pi here, that'd be half a pi, 3/4 pi, pi. Pi thirds would be 2 of these, that'd be 1/3 pi, 2/3 pi, 3/3 pi, which would be pi, okay? This is pi halves, 2/2 pi would be pi. Now notice here, we use a certain little symbol there. What is that? It means a right angle. When you got that, looks like a right angle there, that's exactly what it means. Okay, so pi halves is a right angle. Okay, always. This is what we call a straight angle, pi. Okay, and then all the way around the circle would be 2 pi. These are our key angles we're going to do most of our stuff with, because these are such well-defined angles. Okay, and we'll see they have meaning when we're talking about degrees as well, but we're not there yet. Now, I've already mentioned this, now they bring it up. And I don't know which is the tail and which is the dog, but either this is why we go counterclockwise or this is why we name the quadrants this way. I don't know. But the first quadrant, that's anywhere between 0 and pi halves, that's quadrant 1, because going counterclockwise. Quadrant 2 is between pi halves and pi. Quadrant 3 is between pi and 3/2 pi. And quadrant 4 is between 3/2 pi and 2 pi. But 2 pi is coterminal with that 0. Okay, because it's one complete circle from 0. So this can either be called 2/3 or 2 pi, or it can be called theta equals 0. We usually, when we come in this way, call it 2 pi. Either this is how we name the quadrants, 1, 2, 3, 4, counterclockwise, or this is why counterclockwise is positive. I don't know which was the tail and which was the dog. I don't know which came first. The chicken, the egg. I don't know. Too many analogies. Okay. All right, that gets us to the bottom of 261. Let's move on to, okay. Go back to that concept of coterminal. Two angles are coterminal when they have the same initial side and the same terminal side. In other words, they share a terminal side, coterminal. For instance, the angle 0 and 2 pi, those are the same initial side, same terminal side. Those are coterminal. As are pi 6 and 13 6 pi. There's 1 6 pi, 2 6 pi, 3 6 pi, 4 6 pi, 5 6 pi, 6 6 pi, 7 6 pi, 8 6 pi, 9 6 pi, 10 6 pi, 11 6 pi, 12 6 pi, 13 6 pi. You're right back where you started. Okay? 13 pi 6 is coterminal with pi 6. Now, what's the difference between these two? 12 6 pi. And 12 divided by 6 is 2 pi. What's the difference between these two? Difference between those two? 2 pi. Subtract 0 from 2 pi, you get 2 pi, right? That's the difference. And the difference between these two is 12 6 pi, which is 2 pi. So guess what? If you have two coterminal angles, the difference between them has to be 2 pi or some multiple of 2 pi. So you can find an angle that is coterminal to any given angle theta by just adding or subtracting 2 pi, which is 1 revolution, from that given angle. Okay? Say again? Okay, does that make sense? So, let's say we have a given angle of theta, whatever that is, wherever it is. It has infinitely many coterminal angles, because you can add 2 pi to that, 4 pi to that, 6 pi to that, or subtract 2 pi from that, subtract 4 pi from it, subtract 6 pi. You can go as many times as you want. So if that initial angle theta was pi 6, okay, it's coterminal with pi 6 plus 2n pi. Okay? The 2 pi is because that's how many revolutions you have. N is 2 pi is 1 revolution. N is how many revolutions. It can be 1, 2 pi, 2 pi's, which is 4 pi, 6 pi, 8 pi. Or n could, because N is an integer, n can be negative too. So that would be minus 1, minus 2, I'm not talking. Minus 2 pi, minus 4 pi, minus 6 pi. Whatever your initial angle is, all your coterminal angles are going to be 2n pi from that. I kind of like 2 pi n, but they like to do 2n pi. That's really matter. Okay? Where n is any integer. If n is 0, that's an integer. You just got pi 6. If n was 1, you got 13 6 pi. Okay? Because 2 pi or 12 6 pi. Okay? And so on. All right. So here's example 1. This is in your text. Now, I think I mentioned this when we had the first day of class. I may not have. If I didn't, I apologize. Most pre-calculus books are just about the same. I mean, how many ways can you teach something? I mean, they're all the same. However, I don't like Cengage that much. I know they're giving you a good deal with Cengage Unlimited, but I really don't care too much for Cengage. They usually overprice their books, but now they're giving you a good deal, which is great. I appreciate it. But what I like about this author is he does more auxiliary materials than any other author I've ever dealt with. Okay? One of the things he has is larsonprecalculus.com. That's a website. You don't need the book to buy the book to go to it. Anyone can go to it. Your grandmother could go to it. Okay? It doesn't require a code. No, anyone can go to it. No code required. And this example 1 in your text right under that example 1, it says, see larsonprecalculus.com for an interactive version of this type of example. Now, not all the examples have that, but certain ones of them do. So there's a absolutely free website. You don't need a code. You don't need to purchase WebAssign or anything else. It's free. And you can go there and see them work out and talk about how to do this kind of problem. Okay? So, I wish they didn't show you everything here, but they do. For the positive angle, 13 pi 6, okay, it says subtract 2 pi to obtain a coterminal angle. Now, I don't like the way they did that, okay, because that to me is not obvious. This is obvious. Let me get my pen set up, or at least more obvious. What is 2 pi in terms of 6 of a pi? How many 6 of a pi is 2 pi? Okay. All right. Here's 1 6 pi, 2 6 pi, 3 6 pi, 4 6 pi, 5 6 pi, 6 6 pi. That's 1 pi, right? Say again? That's 7 6 pi, 8 6 pi, 9 6 pi, 10 6 pi, 11 6 pi. 1 revolution, how many 6 pi's is that? 12, exactly. 12 6 is 2, right? So this would be 12 divided by 6. That's 2 pi. Now this I can do. 13 pi 6, that's the angle we started with, and subtract 2 pi from that. Well, 2 pi in terms of 6 of a pi is 12 6 pi. And what do you have? 13 6 pi minus 12 6 pi would give you 1 6 pi. Exactly. Now, to me, this makes more sense than that. I mean, this is true, absolutely. We get everything in least common denominators. Okay? And this is 2 pi. 12 6 is 2. Subtract that from it. So there is a coterminal angle. Here was the angle you were given. Here's one coterminal angle. You can subtract another minus 12 6 pi from it, and it gives you minus 13 6 pi. Yeah, no, minus 11 6 pi. Subtract minus 12 from positive 1, positive pi. Yeah, you would get minus 11 6 pi. Or you could have added 12 6 pi. That would give you 25 6 pi. There's another coterminal angle. So anytime you add or subtract 2 pi or some multiple of 2 pi to that, you get a coterminal angle. So here's your first one. That's 13 6 pi, and then you subtract from that 1 revolution, and that gives you pi 6. Okay? Does that make sense? So anytime you're given an angle and you want a coterminal angle, either add 2 pi to it or subtract 2 pi from it. Or add 4 pi to it, subtract 4 pi from it. Add 6 pi to it. Whatever. I like to get the least common denominators first and then do my subtraction or addition. Okay, does that make sense? Now, here's the B part of that one. What if you started with a negative angle, negative 2/3 pi? Okay, negative 2/3 pi, remember this is 0. Okay, negative 1/3 pi would be down here, negative 2/3 pi would be over here. So here's your initial angle, negative 2/3 pi. How do you get a coterminal angle with that? Add 2 pi to it. But since we're dealing with thirds of pi, how much is 2 pi in terms of thirds? How many thirds of a pi is 2 pi? 6/3 pi? Is it 6 divided by 3? Yeah or nay? Yeah. Okay. Now, folks, I like to think in terms of food. Okay? So let's think of a pie. Okay? Not this kind of pie, but a pie. And what is a 2 pies? How many 6 of a pie do you have? Well, here's a pie and there's a pie. Okay? You divide this into 6. How many you got? 6 sixths of a pi. And this would be another 6 sixths of a pi. Oh, I'm sorry, these are third pi. Let's divide that pi into thirds. Okay? How many thirds of a pi do you have here? 3. How many thirds of a pi you have here? 3. 3 and 3. 2 pi would be 6/3 pi. That's how I think of it in terms of food. Okay? Especially pies. I love pies. Yes. Is it? Oh, perish the thought. Okay? But anyway, here, so you add 2 pi, which is 6/3 pi, to minus 2/3 pi. Minus 2 plus 6 would be positive 4/3 pi. And sure enough, there's 1/3 pi, 2/3 pi, 3/3 pi, 4/3 pi. Yeah, that would be 4/3 pi. Okay. Your graphic shows it. Your algebra shows it. I would have done it this way: minus 2/3 pi plus 6/3 pi gives you minus 2 plus 6 is 4/3 pi. Okay. Now, I wanted to do this one more thing before we leave. Every example, I think, in the text is followed by something called a checkpoint. It's going to be some examples a lot like the ones we just did, but different numbers. I would say as soon as you get out of class and you don't have another class, try to do these checkpoints. Okay? If you get stuck on them, guess what? Audio video solution for in English and in Spanish are located at larsonfreecalculus.com. So not only is this one, the original thing located there, the checkpoint is. The rest of these examples, it'll just be the checkpoints there, unless they happen to have that same thing. So there's another situation where everything you could possibly want is at your fingertips. Try to do the checkpoints. If you can't remember how to do them or figure them out, go to larsonfreecalculus.com. All right, we're going to have to stop there, sadly enough, but Jafari said we had to. Okay, so where we're going to go from here, we erase my previous marks. Okay, we'll start next time with example 2. Okay? Oh, wait, right before example 2. Okay? All right. Now, I'll put this in its place. If you go to the end of 4.1, here you'll have some homework exercises. Okay? Now, these come in groups, so I would say do any of the odds 7, either 7 or 9. Okay? Do 11. It has 2 parts. Do 13. It has 2 parts. Okay? And then do 15. We just did one of those, so you can do that. Stop there, though. Okay? Now, a couple of things. Why do I say do the odd number exercises? 2 reasons. Odd numbers have the answers in the back. So if you do them, go to the back. If you got the right answers, move on. Okay? If you don't have the right answer and you can't figure out how to get that answer, then look here. Right up here at the top. See calcchat.com for tutorial help and worked out solutions for the odd number exercises. So there's another feature that this book has I've never seen another book has. It's calcchat.com. You have larsonfreecalculus.com. This is another one. Anyone can go there. No code required, and you can do any of the homework exercises, get the help. Now, one of these, down here, number 15, that's in red. Number 15, anything in red, and anytime you see these QR codes, if you go click on that, you can actually go to it straight with your cell phone. If you have a QR reader, that takes you to calcview.com, or you can go to calcview.com. Here's another. It presents video solutions of selected exercises throughout the text. So here you have 3 absolutely free sources that you didn't have to buy the book for. Anyone can use them. larsonfreecalculus.com, where your checkpoints are, your calcchat.com, where all your home auto number exercises are from, or your calcview.com, which some of your homework exercises are given in more detail. Lots of possibilities. So do Either 7 or 9 or both, 11, 13, and 15. They're all at Calc Chat. 15 is also at CalcView. All right, good deal. We'll pick up and go from there next time. Any questions? All right. Pretty fast, huh?